must make you take 472 then, right? Are you getting like a math degree? Right? You probably have to take 472 anyway. I see. No, I'm saying good. Yeah.
Okay, let's get started. So this is the second lecture on dynamic programming. Basically, we saw the rough idea of dynamic programming is that you start with a recursion and then you memorize it and it leads to an algorithm. Any recursion can be memorized. The question is, some recursions, when you memorize it, gives rise to an efficient algorithm, right? Even though there is dependence between the subproblems, right? And the key questions, right, that when you think about this technique is, how do you recognize the structure of the subproblems, right? And perhaps this is the hard part. How do you recognize that a problem admits certain kind of dynamic programming solution, right? How do you recognize that? And then the last part is to sort of further optimize, to improve the running time from some specific polynomial time with even better by using some optimization, right? So we saw some examples of when we saw edit distance. We came up with a reasonably simple recursive algorithm, but the main task was to recognize that the number of subproblems is not very large, right? So the task was not so much to think about how to develop the recursion. Of course, you still have to think a bit, but more about how do we recognize the structure of the subproblems, right? So that we know how many, how to store them, how to evaluate them and stuff, right? Now, so why did it work? Or, we also saw some palindromic question, right? We didn't do it in great detail, but so both those problems, edit distance, palindromes, knapsack and stuff, have somehow, for some reason, they admit dynamic programming solutions, right? One of the reasons they do, which we'll kind of emphasize maybe at the end of this lecture, is that they have a very simple linear structure. They look like strings, right? And somehow strings are structurally they're easy to decompose. How can you decompose a string? You can break it into two, you can recursively break up a string by divide and conquer into smaller strings and stuff. And so they have some nice property and that allows for certain class of problems to admit dynamic programming, right? So another class of structures which are easily decomposable but are more general than strings are trees, basically. Okay, and so we'll see today some examples of dynamic programming on tree-like structures, right? And we'll do say a simple example and we'll do a more complicated example, right, to illustrate both this aspect and this aspect. Okay, and with some examples you'll pick up. Oh, so it depends both on the structure of the object that we are trying to solve on and the objective function as well. Okay, both are important, and so let's look at some examples, right? And so this I assume sort of you've heard of this kind of fact, even though maybe we haven't covered NP completeness officially yet. Many graph optimization problems are hard. Okay, we'll see one example, but this is kind of let's say anecdotal evidence maybe, right? Okay, But you know, this maybe you're not so familiar with, you know, but there are many problems, the same problem, if you specialize to trees, it becomes easily solvable. Okay? And again, we'll see examples of that today. And the question is why, right? You know, why is it that, you know, general graphs are hard while trees are easy, right? You know, there must be some reason, right? Well, there are several reasons, but one of the, perhaps the main reason is that trees are easy to decompose, right? You know, you can take out the node, it becomes this easily to decompose a tree into trees and so on, right? So this notion, you know, this is a very simple idea that trees are very special because they are easy to decompose, is a very powerful methodology and has when you do more advanced graph algorithms, the notion of decomposability of a graph is a very powerful notion. Okay, we won't have time to go over this. Maybe if I'll give you a hint about if you're interested, you can look it up. But I'll try to give you a hint of using planar graphs if there is time. Okay, there are things in the notes you can look up if we don't have time to actually go into the details. Okay, so let's start with a very fundamental problem in graph algorithms and with many applications. What's called the maximum independent set problem, right? Many of you probably heard of this problem. So what's the problem? I give you a graph, undirected graph, and a subset of vertices is called independent, or sometimes in operations research and math programming it's also called a stable set, depending on graph theory. It's a set of vertices which don't have any edges between them. Okay? Okay, so what are the independent sets here? For example, D is by independent, right? Because there's no other vertex. Any single vertex is an independent set, right? Okay, what about A and C? A and C, they don't have any edge between them, right? And B, E, and F also are an independent set, right? Yes? Everybody knows what an independent set is? Okay. So, in a sense, it's closely related to the clique problem as well, right? A clique is what? A complete graph, okay? So, basically, if I take the graph and complement it, cliques become independent sets and independent sets becomes cliques, right? So, they're important problems. Okay, so then optimization problem here is, given a graph, find me the largest independent set in the graph. Many applications, very important problem, okay? Well, you know, it turns out that this is not so easy, but let's see. There's even more general version where I can put weights on the vertices, and then I say I want to find the maximum weight independent set. I'm not interested in the previous problem. You just put weight equal to 1 for everybody. Right? This is a maximum weight independent set problem. Clearly, this is even more general than the previous one. And you know, it's an NP-hard problem. We don't know how to find an efficient solution for this in polynomial time, but we don't know whether there isn't one, right? Okay, so you know, what do you do, right? You know, there's a brute force algorithm. You can try all possible subsets of vertices, right? That will take 2 to the n time, right? You can also do you know, what's called branch and bound. You know, brute force is brute force, right? In the sense you're not even maybe exploiting some sparsity in the graph or some simplicity. You know, maybe you can even try to improve brute force by doing something a little bit more clever, and that's you can come up with a recursive algorithm for effectively it's brute force but a little better, right? How do we try to solve this problem recursively, right? Okay, so well, you know, we think of the vertex set as v1, v2, vn somehow arbitrarily, and how do we think? Can we make the problem smaller, right? Can we come with a recursive solution, right, for this problem? Right? How would you recursively solve this problem? So what does it mean to solve it recursively? I want to start with a graph, right, on n vertices. I want to reduce the problem to solving the same problem on a smaller graph, right? Okay? Yeah?
So for given vertices, if that vertices is in the maximum independent set, then we can eliminate all the neighbor of that vertices. That's one case. If that vertices is not in the independent set, we check which of the neighbor of that vertices and to
you're on the right track. You know, in the second case, you just throw it out and then recurse on a smaller graph, right? So okay, so here is what you do, right? You know, you take an arbitrary vertex v1, right? You say, okay, there are two cases, right? You know, I want to find the maximum independent set which contains this vertex v1, and the maximum independent set which does not contain this vertex v1, and then I'll take the max of those two, right? That's the right answer, right? Yeah? Okay, if I want to include v1, what should I do? Well, you know, if I want to include v1, I can't have any of my neighbors, right? So I include v1, so I count that weight, throw away all my neighbors, and recurse on the graph where I remove v1 and the neighbors of v1. Yeah? Is that okay? Okay, so I made the graph smaller, right? Because I threw away, at least v1 I threw away, right? Maybe there is v1 has no neighbors, in which case obviously I should always include v1, right? But yeah, I'm not even thinking, okay, I'm including v1, I throw away my neighbors, even if it is empty set, I at least throw away v1, right? I don't have to, so I have a graph which is smaller, I recurse on that to find the maximum independent set, add it, because I included v1, I add the weight of v1 to myself, right? What is the other case? I don't want to include v1, right? Then I just throw away v1, right? And then recurse on the graph without v1, right? In both cases, I'm making the graph simpler. Yeah? Okay? Makes sense? Yeah? It's very simple, right? So the maximum independent set in the graph is the max of G1, where I don't include v1, or if I want to include v1, I add v1, and then I create a new graph where I throw out v1 and the neighbors, right? And I take the thing. Okay, so this is a very simple recursive algorithm, you know, so that's as simple as that, right? You know, I think there's a typo there. This should be v1, okay? All right. Okay. Okay. Okay, so if you actually do it on, I spent some time drawing this graph at 374, right? So it's actually how to use it. Took me a while. So, you know, if you have a graph like this, you know, if this is which one did I choose here? Can you tell me which vertex I chose to get these two cases? Sorry? This one? Okay, so I chose that vertex, right? You know, why did I choose that vertex? It has a large degree, right? It's, if you want to be heuristic, you can choose a large degree vertex, right? So, okay, so because I chose this vertex, then I can throw away the neighbors, right? You know, that's one case. I throw away myself and the neighbors, that's one case, and I just throw myself out, that's one case, right? And so so what you can see from this is, why is it a little better than brute force? Because it's sort of, you can stop early, you can simplify the instance, right? So this is basically branch and bound, it's called, it's a heuristic procedure. Okay, well, we're not in the heuristic land yet, right? We want efficient algorithms, we are in polynomial land, okay? So the question is, you know, this is a recursive algorithm, how much time does it take? Well, you know, you can write a recurrence which says T of n is T of n minus 1, in which case I'm just throwing one vertex out. The other case is, well, T of n minus 1 minus the degree of the vertex I'm throwing out, right? Plus I spend linear time, right? You know, well, I mean, it's not easy to analyze this recurrence because, you know, this looks a little messy, but in the worst case, you can create a graph where it will take exponential time, right? It's not hard to convince yourself that this takes exponential time. But then I can ask you the question, right? Look, this is a recursive algorithm. What happens if I memorize the recursion? Okay, I can obviously memorize the recursion, right? What does it mean? That means that, you know, I may get as I do this this recursion, I may get the same graph again and again, right? In this recursion, I may get the same graph again and again. So I don't have to recompute it, right? I can store it. Okay, but will that lead to an efficient algorithm? I mean, does the question make sense to you, right? I gave you a recursive algorithm. We already talked about the fact that any recursive algorithm can be memoized, right? So what does that mean in this case? It means that if I start with a graph, how many different distinct graphs will I get, right? An obvious upper bound on that is 2 to the n, right? because there are 2 to the n possible subsets of vertices, and maybe I generate all of them, right? Will I generate all of them, right? How do I know, right? So this falls under the category of the first question, right? That is, I gave you a recursive algorithm, can you understand the structure of the subproblems? And it's not obvious because the graph can be very messy, right, and complicated, right? Does it make sense? Yeah? Okay. That's a valid question, but it doesn't seem like, we can find a structure. And if it does, then we get a polynomial time algorithm, right? If somehow magically only get to generate a polynomial number of graphs in this process, then we'll get a polynomial time algorithm. Okay? But that seems unlikely somehow because it's an NP-hard problem, right? Right? It's unlikely, but doesn't mean it's a proof, right? Okay. So the thing is, you can convince yourself that even for very simple graphs, you'll actually generate exponential number of different graphs in this process. Right? The different graphs you generate will be exponential size, even on a cycle and so on. Okay? So, indeed, you can memorize a recursion, but in general, it doesn't lead to a worst case polynomial time algorithm on all graphs. Right? It's not surprising because it's an NP-complete problem, right? If it's an NP-hard problem, you wouldn't expect it to suddenly magically give you a polynomial time algorithm by this simple recursive algorithm, right? So it's effectively brute force, right? But I'm just illustrating this to say that the reason why you can take this recursive algorithm and memorize it, you don't get an efficient algorithm is because the graphs are complicated. When you take a graph and do some recursion, you get many, many, many graphs. And the number of graphs you generate will be exponential in general, right? So you won't get any simplification. Okay, but now let's say, what happens if you take some very simple graph, right? Some class of graphs, and what are some interesting class of graphs that computer scientists play with all the time? Trees, right? So instead of solving the problem on a graph of arbitrary with no structure effectively, what if I say I want to solve it on a tree? Okay, okay, the same problem, but I want to solve it on a tree. Okay, is it clear? Okay. And here is the thing, and the thing is, it's not obvious even on a tree how to solve this problem. You can't just look at it and say, I'll come up with a simple greedy algorithm or something. It won't work. Okay? Simple greedy algorithms won't work even on trees. Okay? You can try. Right? So, but what is this, right? Even for this graph, you say, what is the maximum weight independent set in this particular tree is actually hard, even though it's a small tree. Okay? Alright. Now, what we can do is, we can try to apply the same recursive algorithm on, instead of working on a graph, we'll try it on a tree and see whether it does anything nice for us. Okay? And I just, for simplicity, I rooted the tree. It's when I think of a graph as a tree, it's not necessarily rooted, right? A tree is a graph, it doesn't have to have a rooted thing, but I just rooted it for whenever we think of trees, usually we think of rooting them because it helps us, right? But in general, a tree is not necessarily rooted. You have to always use this terminology. Let's root the tree. And once you root the tree, it gives you some structure, right? Okay, there's a difference between a tree and a rooted tree. Okay, okay. So what would be a natural candidate to choose in this graph when we try to what is the first node you will try to do the recursion on? The root, right? Because trees are, right? What happens if you do that? Okay, let's see what happens, right? So you choose this. There are two cases, right? We generate, right? What happens when I try to do recursion on this tree? What do? That I choose the root. In one case, I don't want to include the root, so I just throw it away, right? What does it mean throw it away? Remove it from the graph. If I remove the root from the tree, what happens? What is the graph I need to solve it on? Yeah.
Trees rooted at A and B.
Yeah, in fact, I actually want to recurse on this entire graph, right? Right? If I didn't know it was a tree, I'll say I just throw this root out, so I get basically this entire graph without the root, right? But we know that that entire graph is composed of two different graphs which are completely separate. So I might as well separately recurse on this and separately recurse on that, right? Yeah? So okay, so effectively what I do is if I remove the root, I get two problems. I have to solve the problem on this tree and I have to solve the problem on this tree, right? Okay, good. What happens if I want to include the root? If I want to include the root, I include the root, but then I have to throw away my neighbors, which are my children in this case. So I throw away basically R, A and B, then what happens to the graph when I throw all of them out? I'm left with many trees at the grandchildren of the root, right? Okay? So in one case I'm recursing on trees which are rooted at my children, and in the second case I'm recursing on the subtrees rooted at my grandchildren. Okay, now then what happens to them? They will do the same thing, right? Okay, but now we generate again a lot of problems, right? Okay, but now can we say that the number of different problems is small? So every sub problem in this recursion is of what type? A node and its tree hanging below it, right? Those are the only problems that will be generated by this recursion. That's easy to see, right? Yeah? Okay? So why did that happen?
Because each node has only one parent.
Yeah, it's a tree, right? It has some decomposability structure, right? Okay. Okay. So that's the advantage. So we took the same recursion, but we had to choose the node we recurse on a little carefully, right? But then we understand that the only problems that we are generating are recurse on a subtree rooted at any particular node, right? And there are only n of them, right? Okay. So this is what I explained, and there are only n of them. So we give it a name, right? We say, okay, the sub-problems we are generating are, you can index them by every node, right? Look at a node, and tu is the subtree root of t hanging at node u, and opt of u is the maximum weight independent set value in t of u. And then from what we saw in the recursion, what is the value of that? It is one of two cases. You don't include u, in which case you sum over the children of u, opt of v, right? And you include u, that is weight of u plus sum over grandchildren of u, opt of v, right? We just did the recursion, right? Okay, and then we compute these things bottom up, right? Why bottom up? Because to compute the value of a node, we need to know the values of its children and grandchildren. So bottom up means you first do the leaves, because they are the base cases, and then you build up. Okay? Okay. Okay, so now before I go that, do you want me to run an example? Yeah? Okay, all right. Okay, so, the recursion is going from top down, right? But what it means, when we memorize, we are going to go bottom up, basically, right? Okay, so what is the value at 2? So that's what is the maximum weight independent set at a leaf? It's just 2, right? We include, right? There are no grandchildren, so we say, okay, we computed 2. What about, so for all these guys, we can easily know the answer, right? 8, okay. And this is 4, and then what is the next guy we have to pick, right? We have to pick somebody who comes, whose children are evaluated, all that, right? So we look at what is the value of this guy. We don't know, we blindly follow the recursion, right? It's either, we always think, right, what is it? We have the formula, but we just think, okay, there are two cases. Either, I don't include myself, in which case I sum up the values at my children, right? So it's either 9, max of 9, and if I include myself, I'll throw my children out and recurse on the grandchildren, but there are no grandchildren here. So I just get 4, max of 4 and 9, right? So it is basically 9, right? What about this guy? This guy you can check is 11 basically, right? Why? In this case, because if I don't include myself, I get 8 from my child, but if I include myself, I already get 11, right? I don't have, right? So this is the second case example. Okay. Now what about this guy? This guy has grandchildren. So here it's a bit non-obvious, right? We just look at the formula again. Either I include the sum of my children, what is 4 plus 9 plus 9, right? Remember, this 4, 9 and 9 are not the same as this 4, 4, 9, right? These are things that we're computing, right? So what is the two cases? The sum of my children is what? 22, or I include myself 5 plus the sum of my grandchildren, which is 9, right? Max of 14 and 22. So what is it? 22, right? Okay, what about this guy? It is again the sum of 3 plus 11 or 8 plus 8. So it is 16, okay? Okay, now what about the root? Again it is the sum, okay, 22 plus 16 or 10 plus all these numbers, okay? Okay, what is the algebra? Can you do that, the arithmetic for me? So 22 plus 16 is 38, and what is this? 4 plus 9, okay, this is 22 also, right? Okay, 22 plus 14 is 36 plus 10, 46, right? So that is better, right? So I get 46, okay? Okay, makes sense? So what is the running time of this algorithm? What do I need to store? I need to store at each node some number, right? So the space is only linear, right? But what's the running time of this algorithm? O of n. Why? Yeah, so what are we doing, right? At each step we are computing, we are looking at only the children and the grandchildren, right? Okay. Okay. And how much time will we spend on that? Is it constant? We can spend, what is the time I spend at a node? How many numbers do I have to look at, right? I have to look at the sum I do is over my children, right? And then I also have to do it over my grandchildren, right? So I can have a large degree, right? So for example, look at the root, we had to sum up all these guys, right? Okay, what is the naive upper bound of the time I spend at a node? I can spend n time, right? Up to n time I can spend, right? If I have a star, I have to spend n time, right? But the right upper bound is the degree of v, right? Right, the degree of v plus the sum of the degrees of my children. Yeah? Okay, but it can be up to n, it can be small, right? So if you add them up, if you take a naive upper bound and say at each node I spend at most n time, then the total time I spend is at most n square. For sure it's at most n square. But somebody said O of n, and I claimed it is right, the answer is O of n. But it's not obvious immediately that it's O of n. How do I convince you that it's O of n? Can somebody convince me? It's O of n.
For each node, you only wait its 3 counts. Its parents, its alpha,
Yeah.
its grandparent.
Okay, this is called amortized analysis, right? You know, instead of saying, you know, how much time do I spend on each node, let's look at it in a different way and say, when do I touch the value of any node? How many times do I touch it? Okay? So when do I access the value of a node? Well, when I compute it, I have to put it in there, right? So that's one time. But my parent will ask me for my value, right? Then I have to give him the value. But my grandparent also will ask me for that value, maybe, right? So that's it, right? Nobody else is going to ask me for my value, right? Other than myself, when I put it in, my parent and my grandparent. So if you look at it that way, I'm going to access each value only 3 times. Okay? So the total work I do is only 3n, not n square. Even though one guy can spend a lot of time to calculate that value, you can charge the cost of evaluating that guy to the guys that you're accessing. Okay? Alright? See, so what are we saying? Here, look, you know, to calculate the value of r, we had to spend a lot of time, right? But then you say, okay, look, it can't happen too many times, right? Because this guy, you're saying, you know, I'll charge the work to compute this value to this guy, this guy, this guy, this guy, this guy. And each of those guys are spending only 3 times. So this is called amortized analysis. What does it mean? Amortized analysis is an averaging argument, right? Instead of taking the worst case upper bound on one operation and multiplying it by the number of operations, we are doing the counting a little differently. So just the same algorithm, we didn't change the algorithm. Right? The running time is this. Okay, one more small detail which, you know, since not all of you are sort of pure computer science people, when I look at this tree and I say, you know, I have to do leaves first and then this, how do you figure out the order? When you see the picture, it's easy, right? You say, okay, first I have to do the leaves, then which guy comes next? How do you figure out who I should compute the value of next? Right? You don't have a graph. I mean, you're not looking at the picture, right? When you write code, you can't do that, right? So I'm saying, you know, what is a way to sequence the nodes such that the leaves come first and then, yeah?
Can you do a level order traversal and then just run it backwards?
But, you know, maybe, yeah, okay, that's one way of doing it, yeah. The DFS, okay, yeah. Yeah, so every, you know, it's called a post-order traversal of a tree, of a rooted tree, okay, that you can generate using DFS, right? But this is, you know, you haven't seen this before, it's just a useful notion, right? That means that is a way of sequencing, numbering the nodes such that what happens? Your numbers of your children come before your number, right? That's called a post-order traversal of a tree, okay? So if you have a post-order traversal of the tree, you don't have to think, you don't have to worry too much, right? You just have a numbering, and here is a code just to so we just take the post-order traversal of the nodes of tree and then just blindly go through them in that sequence. You don't have to worry about like, oh, what is my, how did I compute my children, right? This is the right way of doing it, right? So it's a very simple code. It's just extremely elementary, okay? Right? Okay, so that's it, all right? That's the maximum. So, okay, what helped, right? You know, what helped is why did it work? Let me abstract it out, right? Why do things work on a tree? The reason why things work on a tree is because every node in a tree is what is called a separator. So what is a separator in a graph? It's a subset of vertices such that if I remove them, you get at least two connected components. The graph falls apart, okay? So in a tree, the root is clearly a separator, right? If I remove the tree root, I'll get, unless it has degree 1, right? Okay, if it has degree 1, it's not a separator, but really, any non-trivial case, the nodes are separators, right? Or in fact, you can find a separator. Okay, so, and we'll also see this useful notion, which, this is just a concept that, if you do any more advanced algorithms, you will encounter. A balanced separator in a graph is a subset of nodes such that if I remove it, I get connected components which are not too big. Okay? Is the notion okay? See, remember, suppose I have a graph which looks like this. Okay? Is this a separator, this vertex? Yes, right? Because if I take this out, I get this component and this component. But it's not very balanced, right? One component is of size 1, the rest of the graph is in one big component. So that's not called a balanced separator. Okay? So for divide and conquer and other reasons, you typically want a balanced separator. What does that mean? That I remove it and I may get more than one connected component, right? But I want to have the following feature, that none of these guys, after I remove this separator S, I don't want any of them to be too big. What does it mean, too big? You shouldn't have more than 2/3 of the nodes of the original graph. So roughly half my graph falls apart into roughly smaller pieces. Okay. Okay. Here is a nice exercise. If you have not seen it, it's a nice exercise. Prove that for every tree, there is a balanced separator. Not just any separator. Balanced separator. See, every tree has always one node that if you remove it, you will get components which are not too big. Okay? Okay, this is a very simple exercise that sometimes we give in discrete math or even in algorithms courses, but if you've not seen it, try it. Okay? It's true even if you put weights on the nodes. There is always a balanced separator. Okay? Okay, and then we'll come back to it, right? Let me do one more example, right? How many of you have heard of the dominating set problem? No? None of you have heard of the dominating set problem? Okay, then you learn more than what I expected, right? Okay, so you also learn a new problem. Okay, it's a very important problem. It's actually a very, very nice problem. Okay, I mean, it comes up in many applications, right? Okay, so what is a dominating set? A dominating set, as a sort of word should kind of give you a hint, think of an application that will motivate, right? I have a graph, right? Think of the graph as a network, for example, right? It is some network of computers or sensing nodes or something, right? And you want to put select some nodes, right, such that they can watch all the nodes in the graph. Okay? So there are different ways of thinking about that. So one way of thinking about it is I want those nodes, what does it mean to watch all the nodes, right? That means that for if you are in the set, then clearly you can watch yourself, right? Okay? But if you are not in the set, you should be adjacent to somebody in that set so that he can monitor you. Does it make sense? Okay? So here is an example. So formal definition is that a subset of the vertices is called dominating set in the graph. That means they can watch everybody, right? What does that mean? That is, every vertex should be in the set, or if it is not in the set, some neighbor of it should be in the set. Okay? Is the definition clear? Okay. So, okay, clearly if you take all the vertices, it's a dominating set, right? Yeah? I mean, that's by definition, because there is nothing to do, right? But you don't want a large dominating set, because that is not the point, right? If you take everybody, then it's not very useful. What you want to see is that you want to see, can I find a small dominating set, right? So that I don't want to choose too many nodes, but they can still monitor everybody. Yeah? Okay? Okay, what are examples here? Clearly, give me another example of a dominating set. Since it's not a well-known notion to you, I just want to give me another dominating set in this graph. Yeah? BE? BD. Okay, so he says, let's choose this and this. Is that a dominating set? Okay. What about another one? Sorry? EF. Is EF a dominating set? No, right? Why? Because B won't be seen, right? Okay. Okay, how about ACF is a dominating set, right? So for example, I can choose this, this, and this, right? Yeah? Okay? There are many dominating sets, right? Okay. So what is the dominating set problem? I want to, and I can have weights also, right? And I want to find the minimum weight or minimum size dominating set in a graph. Okay? Alright? It's again a classical problem, many applications, very important. It's connected to set cover. If you have not heard of set cover, it's a very nice problem. A lot of graph theory algorithms and stuff. It's an NP-hard problem. Okay? Okay. So we don't expect it to be able to solve it in a graph, but let's try to solve it on a tree. Right? Okay. So here is the same tree, and I want to fall in the dominating set in this tree, right? Okay. So let's try the same kind of rough approach we tried before, right? We know the trees are nice because they fall apart, right? Nicely. So let's see now, does it work for dominating set to solve this little different problem, right? Remember, in dominating set, it's a minimization problem, not a maximization problem, right? We're trying to find the smallest dominating set so that it covers everybody. Well, in independent set, you're trying to find the maximum size thing, right? The problems are different, right? The objective function is different. The definition of what is a feasible solution is different, right? Okay, so you have to, it's not obvious that you can solve this problem also on trees. And in fact, we'll see it's a little tricky. So what is the natural thing you want to do when you try to do recursion on this, right? We can try the same kind of approach. We look at the root, because the tree falls apart, so it's a natural thing. The structure is telling you, try to do the obvious thing, break apart the tree, right? Okay, if you try to include, what is the thing that you like to do? You'd say, let me try to include the root or not include the root and see what happens, okay? Okay, what happens if you try to include the root? So, okay, I want to include the root in my dominating set, okay? So I included the root, so it covers itself, but it can also cover the children, right? Okay, so what do you want to do with that? Sorry? Okay, so okay, that's why you have to be careful, right? This is why the problem is tricky. That's what I want us to think. I include the root, which means I cover myself and I cover my children. Does that mean that I can throw away my children? Maybe the children is needed to cover the grandchildren. Okay? So I don't know what to do actually. If I mean, in the sense that I can't simply say I included this, even in the case when I decide to include the root, I can't simply recurse on the grandchildren. Okay? Suppose I recurse on my children. Okay? What does it mean if I recurse on the children? I've forgotten the fact that I've included the parent of myself, so I don't have to necessarily to include the, I can't recurse on the tree rooted at one of my children, because then maybe I don't need to include the root of that, right? So I can't just break it apart, even in the case when I try to include the root. Okay? Now that's already we say, wait a second, this looks a more difficult problem, right? What if I try not to include the root? I mean, let's look at the case, right? I don't want to include the root. Okay? Then what should I do? Sorry? But I don't need to include all the children. I have to include at least one child. But it looks like a big mess, right? Okay, even on a tree, somehow it's not easy to solve this problem. Okay? It looks like that, right? Now why is that? Because even though removing the root decomposes a tree, there is information that I need to know between, I can't decompose the problem so easily. To solve the problem recursively on the children, they need to know what's happening up at the root, right? And they need to also know, in some sense, even when I include the root, the child has to know that the root has been included, right? That's one reason. And if I don't want to include the root, the children have to coordinate and say, which of us is going to cover the root? Because at least one of them has to cover the root, right, if you don't include the root. So I can't recurse on my children or my grandchildren so easily. Okay? Okay, so this is why, dynamic programming is tricky for people, right? You can still solve this by dynamic programming, but it is not as obvious anymore. Okay? Okay. So how do we figure out how to decompose this problem, right? And we realize that the obvious recursion is not working, so we have to try something a little bit more, right? Why is the obvious recursion not working? Because there are dependence between the children. So now we have to say, remember the knapsack problem, right? We try to decompose it, and we realize that if we can't just recurse on these items and these items because the knapsack capacity is making them dependent, right? So the thing we have to try is, can we incorporate the dependence into the recursion by adding additional variables so that then we can decompose? And the question is, what variable should we add? And how is the size of what we are adding? Okay? So it's a little tricky. So this is a non-trivial example. So how do I think, right? As an experienced person, how do I think about these problems, right? So here is what I think. Okay? Let U1, U2, UK be the children of the root of the tree. Okay? Okay. I say, okay, what information do the children need to separate themselves? Okay, remember, the tree is decomposable, but the problem is preventing us from recursing on the children. But I say, okay, what information do the children want? Right? Well, first I want to know, is the root included or not, right? That makes a difference, right? As a child, if I know that the root is included, I will do something else as opposed to if the root is not included, right? Why is that? Because to recurse on the children, I need to know if the root is included, the child, this problem knows that I don't have to cover the root of myself, right? Because my parent can cover me, so I can save something, right? So at least it needs to know whether the root is included or not. Okay? The other thing I need to know is that in the second case, if the root is not included, I need to know that at least one of them has to cover, right? Okay? Which one? Okay. So the minimum information that the child needs is, should I cover the root or somebody else will cover the root? Does it make sense? I need to know, am I responsible for covering my parent or will another sibling take care of the parent? Okay? All right? Okay, so these are the two pieces of information that I need, right, to kind of go down and separate and do my own thing, right? Okay, so since we are not able to decompose the problem because of this dependence, we will shove the dependence into the recursion, okay, and solve a more general problem. So here is what we do, okay? So in addition to so we'll think of two Boolean variables, okay? One is my parent included? That's why I just put pi here. Don't get confused with pi, right? You know, pi, shorthand for parent included. It's a Boolean variable telling me is my parent included or not, right? And the second variable is, am I responsible for covering my parent? Okay? That means that should I include myself because I have to rest, right? So I know that I need at least that much information to separate the problem, but it's not even clear that that is sufficient. Okay? So, but we'll try with additional variables and see if this will help me, right? So, okay. So what I am trying to tell you is that consider this value. What is this? Opt. I want to solve a problem at a child, not just independently, but under two conditions. All possibilities of the following things. I want to know the value of the optimum solution to dominate all the children in TU with two additional variables. One variable, two Boolean variables which tell me whether I should include whether my parent is included and whether I am responsible for covering my parent. Okay. So just to give an example, what does opt U10 mean? Opt U10 means that I want to find the minimum weight solution in the tree TU under the condition that U's parent is already in the solution and that U is not responsible for covering it. Well, if U's parent is included, he is not anywhere responsible for covering it, right? But just to keep the variable simple, we do that. And what is the final solution we want? We want opt R00, right? What does opt R00 mean? R doesn't have any parent, right? So there is no way the parent is going to help him. And he is not responsible for covering his parent because there is no parent, right? That is the right value we want to compute, right? Okay, we are trying to solve more general problems than what we initially thought we wanted to solve. Why? Because it will help us decompose the problem. Otherwise we can't decompose the problem, okay? Okay? This is a bit non-trivial, I see that, right? But that's why I'm doing it, right? Okay, so how do we, okay, so here is the thing. Sure, if we can solve these problems recursively, then it's good, right? Why is it good if we can solve these problems recursively? Then the number of problems is not very large, right? Because it is n times 2 times 2. The number of problems is still O of n because we want to solve all, these are the sub-problems that we need to solve. But to be able to solve these things, we need to see if we can actually solve them recursively. Can we express these things recursively, right? What does it mean, right? Here is an example, right? Let's see. It's a long slide, but let's go slowly. This is a very important topic, right? Okay, what does opt U00 mean? The meaning is very important. Opt U00 means it is the value of the minimum cost dominating set in the tree TU where my parent is not included, right? 0 means parent is not included. Another 0 means I am not responsible for covering my parent, right? Okay, so how do we calculate opt of U00? Can we write a recursive relationship for that? Well, there are two cases. Now let's consider those two cases again. I include U and I don't include U, right? Let's see if this helps, this extra information helps us compute this thing, right? If U is not included, if U is included, what does it mean? I have to count the cost of including U, right? So that is opt of U00 is the weight of U plus, what should I do? I should recurse on my children, right? Okay? Okay, when I recurse on my children, what am I going to tell the children? I included myself, right? So I am recursing on my children and telling them, look, since I included myself, your parent is included. So I put opt of V1, and since I included myself, there is no need for you to help me, right? So opt of U00, if I want to include U, is W of U plus the sum over the children of U, opt of V10. Okay? Okay? Agreed? Okay, what about opt of, the second case is U is not included, right? Okay, if U is not included, my parent is not included, right? U00 means that my parent is not included. That means my children have to dominate me, right? Okay, at least one child has to dominate me. Yeah? Okay, which child? I don't know, right? Okay, do I know which child? I don't know. So what I do, I try over all my children. So I pick one child and say, okay, you cover me. Okay? And so I say, okay, if I chose that V, then I'm telling him, look, I didn't include myself, you better cover me, right? And the others you don't have to cover me, right? Because if I pick one guy, it's enough, right? Okay, so which child should I pick? I have to basically try all children because I don't have a choice, right? I don't know which one will lead to the optimal solution, right? So remember, this expression is complicated. It's the min over all the children. I'm forcing this child to cover me, and I'm telling the other children you don't have to cover me. Okay? But this is the min over all this thing. Okay? Now what is opt U00? Well, it is the min over this and this expression. Because I don't know whether I have to include you or not include you. Okay? Yeah?
Why not pick up two children to cover?
No, so this simply means that that V prime could be included. So I'm saying, okay. So I'm not forcing this guy not to include himself. I'm giving him the option of not including himself. See, what is the meaning of opt U00? It simply says that you are not, 0 here means that you don't have to include yourself. You can include yourself if you want, but you don't have to force yourself to be in there to cover your parent. That's all it means. So this doesn't mean that all of these guys won't be in the optimal solution. You can have two of them also. But at least one of them has to be there, right? So I'm forcing that guy one guy to be there and giving the freedom to other guys. Okay? Yeah? Okay, now what is the moral of this? The moral of this is once we included extra information, we're able to actually go through the recursion, right? Because we remove the dependence, the additional information is helping us remove the dependence, right? Okay? Alright, let's do another case. We have to do it for all the cases now, right? It's not enough to compute opt U00, right? We have to compute what is opt U10. What does U10 mean? Use parent is included, and in which case, I am not responsible for covering him. I'm not responsible. It's obvious here, but I don't have to include I'm not responsible for covering the parent. It anyway is included. Okay, so even here it's a little tricky. So let's go through the case, right? So what is opt U10? Well, again, there are two cases. Case U is included. If U is included, well, we pay for it. Then what should I do? I recurse on my children saying that your parent is included. You don't have to cover me. Right? Make sense? Huh? Okay. Now that's not a very, that's an easy case, but what if U is not, we don't decide not to include U? This is an interesting case. If U is not included, remember, we are in the case opt U10, right? What does it mean that U's parent is included? Okay? And I'm not including myself, including you, right? But what should I tell my children? You don't have to worry about me, right? So what am I telling them? Look at the children and simply saying V00. Okay, this is an interesting case. Why did I call them V00? Because I'm saying, okay, I'm not including myself, but you don't have to bother covering me because my parent is already there. Okay? Do you understand this case? Okay? So then we take again the min of these two. Okay, nice, no? Okay? Okay. So some people may say, oh, not including you may appear to be always advantageous, but it's not true. Right? Okay, people will think greedily in this case, but you shouldn't use greed here. You should just follow the definitions, right? Okay. Now what is the third case? Okay, so we have to do all this, there is no choice here, right? Opt U01, what does opt U01 mean? Parent is not included, but I am responsible for covering my parent. So what should I do? I have to include myself, right? There is no choice in this matter, right? If I am responsible for covering my parent, I have to include myself, right? There is only one case, right? Okay, so opt U01 is I have to include myself plus the sum over my children opt V10. Why V10? Because I included myself, so they don't have to cover me, right? And right, that's it. So, but I'm telling them, since I am including myself, you can save some money if you want, right? So does it make sense? Okay. Now there's a last case which is actually unnecessary. Opt U11. What does it mean? U11? That I include myself and I am covering the parent, but it's kind of a redundant case, right? So okay, so let's recap, right? You believe that, so there are only three interesting cases, opt U00, U10, opt U01, right? So in fact, you can suppress all this and call this, create only one variable and say case 1, 2, 3. Okay, you can call them 00 is case 1, 00, and right? Okay, but then that hides this is more useful to think clearly and say what is the information that I need to exchange between the children to decompose, right? Okay? Okay. So, what are the base cases? If U is a leaf, opt U00 is simply the weight of U, right? Because the parent is not there, I don't have to cover, but I have to cover myself, right? So, right? Opt U10 is what? My parent is included, right? And I don't have to cover it, so I just did 0. Right? If my parent is included, I don't have to do any work, right? Because I don't have any children to cover. If opt U01 is what? I have to cover my parent, so it's weight of U. Okay? Let's say, is it okay? And then again so at each node, what are we maintaining? We're maintaining 3 values now, not 1, right? Opt U01, opt U00, opt U, so that my parents can use that information, okay? Okay. And finally, what do we need to output? Opt R00, right? That is the final optimal solution for the minimum dominating set in the entire tree, right? Because R doesn't have any parent. Does it make sense that this is what we need to compute? Yeah? Questions? Okay. And the total time, again, you can using bottom-up computation, you can check is O of n, right? All right. Okay. 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 Let's recap the process, right? The tree is allowing you to decompose the graph, right? But the objective function is causing trouble, right, in the dominating set. So how did we think about that? We thought about what information do I need to keep track of to be able to decompose the problem, right? Okay. Now you can go back to the independent set problem and also think about it that way, okay? In fact, it's instructive for you to actually go back to the independent set problem and think this way, right? This is a more general way of thinking about dynamic programming, right? How do you figure out a dynamic programming solution? You have to first think about the structure that you're decomposing. It could be a string, it could be something else. This is one way, I'm not saying this is the only way, right? And then you ought to also think of the objective function and say, how do I put additional variables into the recursion to actually allow me to solve the problem recursively, right? So that's the, and you'll see some examples of that, okay? Questions? Okay? Yeah? Yes? Okay. All right. I'm going to tell you a little bit about separators and planar graphs. This is kind of a bit of an advanced topic. Part of the thing in teaching a class like this is to expose you to important concepts which we may not be able to go in detail in this class, but it will pique your interest and you sort of see some connections to other more advanced topics, and it's good to gather some facts as well along the way. Okay. And I also want to show you that this paradigm of decomposing the trees is actually much more powerful in allowing you to decompose graphs. So everybody knows what a planar graph is, yeah, sort of, right? is a graph that you can draw on the plane, right? Formally, what does it mean? That you should be able to put the vertices on the plane, and edges should be curves on the plane connecting those vertices, right? And those no two of them should cross, right? Why are planar graphs interesting? Well, they have many. It's natural, right? We live in 3D. 2D is kind of what we draw on, right? Since we're kids. But that's not the only reason why planar graphs are interesting, right? They're also very, in some sense, the surface of the Earth is 2D, right? So, in a way, many of the networks we build are inherently nearly planar, right? That's just space, right? And so they come up in applications. The planar graphs are sort of like good model for any practical networks. And they are very important for one reason or the other, for reasons which are not completely obvious. They come up in structural graph theory independently, okay, for some other reason, right? It's too hard to explain that. So there are many beautiful properties. People study them in all kinds of areas, right? From pure math, algorithms, applications, for many things. I'll tell you a few interesting facts about planar graphs. Many of you have probably heard about Euler's theorem on how dense can planar graphs be, right? Okay, the planar graphs can't be too dense because the edges will cross, right? How many edges can you have in a planar graph? Well, Euler's theorem tells us that you cannot have more than 3v minus 6 edges in a mini planar graph, and this is achievable, okay? So in particular, what does this mean? It means that because the average degree is only little less than 6, there must always be a vertex with degree at most 5, okay? Every planar graph has always a small degree, a vertex with small degree, okay? So if you remove that, you still have a planar graph, right? Every subgraph of a planar graph is also planar, yeah? That's obvious because you can take it out, it's still in the plane, right? So you can again find another vertex which is of degree 5 after you remove the first vertex of degree 5, right? Again for the same property. So you can peel off one vertex at a time with degree 5 in this graph. This is called 5 degenerate. If you don't know about that, don't worry. Maybe many of you have heard of this Kuratowski theorem, right? How do you tell whether a graph is planar or not, right? Well, there are two ways of thinking about it. One is algorithmic, right? One is you can say, given a graph, can you give me an algorithm that will test whether the graph is planar or not, right? Can you draw it on the plane? Right? I just give you edges and nodes. Can you draw it on the plane? And if it is, you draw it and tell me it is in the plane. If it is not possible to draw it on the plane, tell me no, you can't draw it on the plane. How do you tell that? Okay, that's a very non-trivial question, right? And what did Kuratowski prove? Kuratowski proved that a graph is not planar. He gave a characterization, right? If and only if it doesn't have two graphs sitting inside it. Okay, what are those two graphs? K5. What is K5? Complete graph on 5 vertices. Okay, you take the 5 vertices. The first claim is that this graph is not planar. Okay, did I not include all the edges? One is missing. Okay, all right. Okay, so that's not planar graph. Okay, it's kind of hard to convince yourself, but you can try all possibilities. Okay, what is the other graph that is not planar? It's called K33. You take a complete bipartite graph on, okay, I make sure I draw all the edges. Did I draw all the edges? No, here, right? Okay? So, okay, these two are not planar graphs, and Kuratowski proved that basically if the graph is not planar, these are sitting in your graph. Okay, I won't tell you how they're sitting in the graph, but that's okay. Using that, many years later, Lipton and Tarjan showed that you can find a linear time algorithm to check whether a graph is planar. Very nice algorithm. Okay, doesn't matter. Okay. Everybody have probably heard of the 4-color theorem of our planar graphs. So every planar graph can be colored with 4 colors. Okay, what does that mean? That you can color the vertices of the graph with 4 colors, such that for every edge the 2 endpoints have different colors. That's called a coloring of a graph. It's not hard to use this property to show that every planar graph is 6 colorable, because you take out a degree 5 vertex, color the rest of the graph, and put this vertex back. How many colors do you need? Oh, maybe all my neighbors have 5 colors. So then I have to use a 6th color. If I have 6 colors, you can always color a planar graph using this property. But the fact that you can color it with 4 colors is not very easy. Okay, so it was a conjecture for a long time, and then finally it was shown at in the Illinois math department. It's a very famous result. They used computers to solve this problem. So that was also very controversial because the first time actually they reduced it to some number of 1,000 or 2,000 cases. Okay, and then they used computers to solve this. This is in the math department here. It's a very famous result. Okay. And people didn't like it. It's a fundamental mathematical theorem, and then why do you need to use computers to solve it 2,000 cases? But still, even today, we don't have a pure math proof of this. The number of cases have been gotten down to some 100 or something. But still, you have to do 100 cases, I mean, not actually 100, maybe 500, right? But still, the only proof known is this computer-based proof. I mean, in the sense that you have to enumerate a lot of cases, right? Getting down to those cases is not easy, but okay? And perhaps one of the most important theorems for algorithmic purposes is what is called the planar separator theorem. Okay, what is a planar separator theorem? The planar separator theorem says that every planar graph, there is a set of size square root n vertices. If you remove, the graph will fall apart into, it's called a balance separator. It will fall apart into connected components. Okay, so take a complete graph. Okay, take a complete graph on n vertices. Can you break it apart into balance separator with small number of vertices? Okay, so if I take a complete graph of n vertices, right, you don't have a balance separator of size less than n over 2 basically. Okay, you need almost entire graph to split apart that graph. But planar graphs are very special. They have this square root n size thing. Okay, okay. Now why am I telling you all this thing, right? I mean, it's fun, right, for me at least, right? Right? But I want to illustrate the dynamic programming. That's the whole point of this, right? So, okay, remember if I want to solve the maximum independent set problem in a general graph, we can do brute force, which takes what, 2 to the n time, right? Okay, you can actually do it slightly better, and this is completely non-trivial. Okay, you can solve the problem in 1.889 to the n time, and you may think that seems like, oh, 2 to the n versus this, that doesn't seem like a big deal, right? This is not easy to figure out. Okay, all right. Okay, okay, you can do slightly less than 2 to the n, and it is believed, under some assumptions that you need exponential time in n to solve maximum independent set. However, if you give me a planar graph, you can solve the problem in much less time. 2 to the square root n time. Okay, you may think, okay, this is still a bit bad, right? But this is much better than 2 to the n, right? If n is take n to be 100, right? 2 to the n is 2 to the 100, roughly, right? Well, not roughly, less because of that algorithm. But if the planar graph is n size and square root n is only 10, no? So it is maybe feasible to run this on some graphs of smaller size, right? If you want to solve it on a planar graph. But forget about the practical utility of this or whatever, right? It is the fact that it is a bit surprising. What is it that you took advantage of to get this faster running time? Okay, that's what I want to convey, right? Okay, it is basically dynamic programming. Okay, on what? Okay, that's the key thing, right? So here is the thing. So I'll use what is called okay. So every planar graph, or in general, if you have separators, you can do the following decomposition. Okay. Okay, so I give you a planar graph. Remember, what is it that we talked about the planar graph separator theorem? It says that there is a set of size square root of n, some constant times square root of n, such that if I remove, the graph falls apart into smaller pieces, right? So this is the separator S, then I get smaller graphs, right? G1, G2, some Gk. Okay,